Welcome back to Physics 425. In the last video, what we were talking about was the grand canonical ensemble. In this ensemble, we have replica systems that are in thermal contact with one another so that they can exchange energy among the systems that are part of this ensemble. But also, the systems are allowed to exchange particles. And so the ensemble itself acts as both a thermal reservoir and a particle reservoir, but any member of the ensemble can have its energy or particle number change. And what we calculated was the grand partition function, and so it involves a sum over all quantum states, and we could have different energies and different particle numbers. The grand potential is minus kBt times the ln of this grand partition function, and it's useful because we can use it, I think there's usually a subscript g, we can use it to calculate thermodynamic properties. So for example, in today's video, we're going to use the grand potential to calculate the average number of particles in a given state. In fact, what we're going to do is we're going to try to derive both the Fermi-Dirac and Bose-Einstein distribution functions, which we've used before, but let's see if we can come up with a fundamental derivation of these quantities. So let's consider a single energy level, and we'll assign this energy level an energy of epsilon. And let's say that this level can be occupied by either 0 or 1 particles. So we're going to try to put fermions in this energy level, and there can only be 1 or 0 fermions in this energy level. Okay, so in one case, we have the level occupied, and in this case, say N1 is equal to 1 particle, and the energy, say U1, is equal to epsilon. The other case, of course, is that this energy level is empty, and in this case, N0 is just 0, and the energy U0 is equal to 0. Okay, so if we were to calculate the grand partition function, what we would do is we'd have to sum over all of the possible states. In this case, it's relatively simple because there's only 2 states. Either the level is occupied or it's unoccupied. So in general, this grand partition function takes the following form. And in this specific case, there's only two terms. So one of the terms is nj is 0 and uj is 0, so we have e to the 0, which just gives us a 1. And in the second case, uj is going to be epsilon and nj is going to be 1, so that the second term is e to the minus epsilon minus mu over kBt. All right, so if we were to construct the grand potential, we would just take minus kBt times the ln of this. And so we're going to have the ln of 1 plus e to the minus epsilon minus mu over kBt. Okay, so the average number of particles is given by the derivative of the grand potential with respect to chemical potential. And so it's the negative of that. So let's start by evaluating this derivative. So we're going to get minus kBt, and then we have to use chain rule. So when we take the derivative, the ln becomes 1 over 1 plus e to the minus epsilon minus mu over kBt. And then we have to multiply by the derivative of what's inside the ln with respect to chemical potential. And so let's see, there's a negative minus mu, so that becomes positive. So we should pick up a 1 over kBt, and then we get the exponential back again. Okay, so let's see, the kBt factors cancel, and we end up with a minus e to the minus epsilon minus mu over kBt, and then we have 1 plus e to the minus epsilon minus mu over kBt. We can simplify this a little bit. Let's multiply the top and bottom by the same factor, and we'll make this e to the epsilon minus mu over kBt. And as long as we multiply by 1, we can do that. So we'll multiply top and bottom by the same factors. And so this is equal to, let's see, minus 1 over e to the epsilon minus mu over kBt plus 1. Okay, so n bar, and this is going to be for fermions, and so this will be the Fermi-Dirac distribution, is going to be equal to minus this derivative of the grand potential with respect to chemical potential, and so that just eliminates the minus sign, and we get our result. This is 1 plus e to the epsilon minus mu over kBt. And this is our Fermi-Dirac distribution function, which we've used before, and now we have calculated from first principles. So this is the Fermi-Dirac distribution. So it tells us the average number of identical fermions in a state of energy epsilon at temperature T. Okay, and so if you have, say, for example, spin 1/2 fermions, you could have one spin up and one spin down in each state. But those fermions aren't identical because they have different spin states. Okay, so let's just think about this a little bit. And so we've seen these plots before, but let's do it again. Let's plot this Fermi-Dirac distribution versus epsilon for the t goes to 0 limit. So if epsilon is greater than the chemical potential, so epsilon minus mu is positive, then this exponential is the exponential of a positive large number if we set t goes to 0, and so e to a large positive number is very large, and so this goes to infinity as temperature goes to 0, and therefore the distribution function is 1 over a very large number plus 1, which just goes to 0. Okay, so we can start to make that plot. And so here's epsilon, here's the chemical potential mu, And we considered the case where epsilon minus mu is positive, and so that is this region, and we said that in this case the average number of fermions goes to 0. So this is the average number of fermions in that state goes to 0. Okay, so the other case is, of course, epsilon minus mu is negative. And so then if we have e to the epsilon minus mu over kBt, if t goes to 0, then we have e to the large negative number, and this exponential goes to 0 in this case, and the Fermi-Dirac distribution is 1 over the exponential, which goes to 0, so it vanishes, plus 1. And so what we have is 1 over 1, which is just 1. And okay, so if this is 0 and this is 1, for energies less than the chemical potential, the Fermi-Dirac distribution is just equal to 1. And then there's a very sharp transition right at epsilon equals mu. And so this is the t equals 0 case. If you start to increase the temperature, all that happens is you start to blur out the sharpness of this transition. And so this is t greater than 0. And then if you increase temperature even more, you just blur this out even more. And so this is, say, some temperature, say, even greater than 0. Okay, so that's the Fermi-Dirac distribution. If we had a single energy level and we were going to fill it not with fermions but with identical bosons, then we can put any number of particles in that energy level. And so we ask the question, what if we could have any number of particles? Look, I should be saying identical particles. In a quantum state of energy epsilon. Okay, so the way that we calculate the grand partition function is the same. We have to sum over all of the possible states, and the sum is e to the minus epsilon j minus mu nj over kBt. But now what we could have is like an empty system where n is equal to 0, epsilon is equal to 0, or we could have one particle, and so n is equal to 1, epsilon is equal to, well, maybe let's do it this way. Let's say the energy is equal to 0, and so in this case energy is equal to epsilon, and then we could have two particles, so n equals 2, and energy is equal to 2 epsilon, and this just goes on and on and on until we've used up all n of our particles. And so eventually we have however many particles there are, and so there's n particles, and the energy is equal to n epsilon, and then it could keep going, right? We said we could have any number, so we could have n plus 1 and so on. It just keeps going up into infinity. Okay, so if we were to write out some of the terms of the grand partition function, we're going to have the case where epsilon and n are both equal to 0, so we get a 1 plus, and then we have one particle, And then we have two particles. And so we have an energy of 2 epsilon. And we have n equals 2, so we could factor out that 2. And then it keeps going, and then we get to n particles. And then we could have n plus 1 particles, n plus 2 particles, all the way up to infinity. Okay, we could rewrite this in another way. I'll write the first two terms exactly as they were. But let me write this third term as e to the minus epsilon minus mu over kbt squared, right? That's the same thing. If I square an exponential, that's equivalent to having e to the 2 times whatever was in the exponential. And then we get to the nth term. I could write that as e to the minus epsilon minus mu over kbt to the n plus and so on. And so when it's written in this way, you might recognize this as a geometric series. And so this is a geometric series of the form of, say, sum from q equals 0 to infinity of r to the q, which has a definite solution. That sum is equal to 1 over 1 minus r, provided that the absolute value of r is less than 1. Okay, so in our geometric series, the grand potential is a geometric series with r equal to e to the minus epsilon minus mu over kbt. Okay, and so long as epsilon minus mu is a positive number, so if epsilon minus mu is positive, then we have e to the minus a positive number. Doesn't matter what temperature is. And so, in other words, we have 1 over e to a positive number. And that's always going to be something less than 1. So if this epsilon minus mu is positive, then we could evaluate this grand partition function as being 1 over 1 minus r, and so this r is e to the minus epsilon minus mu over kbt. Okay, good. So next, what we can do is we can write down the grand potential. I think we may in a future assignment actually confirm that this is in fact the case. So it is true that this condition is met. We might do it in an assignment, but let's for now just assume that it is the case so that we can proceed. So the grand potential is minus kbt times the ln of the grand partition function, which we could write equivalently as kbt over the times the ln of 1 over this grand partition function, which is kbt ln of 1 minus e to the minus epsilon minus mu over kbt. Okay, good. So that's the grand potential. Now, just like we did for the fermion case, we can calculate the Bose-Einstein distribution function using minus the derivative of the grand potential with respect to the chemical potential. Okay, and so let's see, we're going to get kBt, and then we should end up with, well, there's a minus sign out front from this minus sign, and what we can do then is do the chain rule. So the ln gives us 1 minus e to the minus epsilon minus mu over kBt. And then we take the derivative of what's inside. We pick up, let's see, there's a 1, 2, 3 minus sign. So overall we get a negative. We should get a 1 over kBt. And then we get the exponential back again, e to the minus epsilon minus mu over kBt. Okay, and so we can cancel the negative sign, and we can cancel a kBt, so that this Bose-Einstein distribution becomes e to the minus epsilon minus mu over kBt 1 minus e to the minus epsilon minus mu over kBt. And now what we can do is we can do what we did before. Let's multiply the top and bottom by the same exponential. We just reverse the sign in front of the argument of the exponential, and then we get the final form of this Bose-Einstein distribution, and it looks like 1 over e to the epsilon minus mu over kBt. And in the Fermi-Dirac distribution, we had a plus 1 in the denominator. This time we get a minus 1, and that's the important difference. Okay, and so this is the average number of bosons in a state of energy epsilon at temperature T, and it's the Bose-Einstein distribution. All right, good. I want to do one more thing today, and what I'd like to actually look at is the case of a classical gas. So, this is a low temperature course, but I want to just briefly take a look at classical gases. And so this is a gas in the dilute limit, so the density of particles is not very high, and at relatively high temperatures. And so to start this discussion, I want to remind you of the entropy of a monatomic ideal gas. So ideal monatomic gas entropy is given by this so-called Securer-Tetrode equation. So this equation takes the form of S is NKB, and then I'm sure you've seen this somewhere before, but there's a bunch of terms here. There is the ln of V over N, and then there's a 3/2 ln of, I'm going to write it in this way, M times the internal energy over 3 pi h bar squared N, and then there's a 5/2 here. Sometimes, or often maybe, if you had a monotonic gas, you would write the internal energy as 3/2 NKBT. And if you did that, this term in the argument of the ln would be mkBt over 2 pi h bar squared. And so this is often written in the shorthand notation of 1 over lambda d squared. And so we'll come back to this in a second. I've written this equation where I've left the internal energy U inside the lawn, and I've done that for a reason. And the reason is that we're going to use this entropy to determine the chemical potential. So we can determine the chemical potential of this classical ideal gas from mu is equal to minus T times the derivative of the entropy with respect to n, but we have to hold the internal energy and volume constant. And so, see, the reason why I didn't want to write U as 3/2 n kBt is because then when we evaluate the n derivative, I wouldn't be able to hold U constant because I would cancel the n with the n in the denominator here. So I've written this in terms of the internal energy so that I could hold it constant when I evaluate the derivative. Okay, so let's just first start with this derivative at constant internal energy and volume. Okay, so first of all, there's an n out front, so there's a coefficient n, so we get kb times all of the stuff that was already there. So I'm just rewriting all of these terms. Okay, and so now we have to take the n derivative of the things that are inside the braces, and we can see those terms here. So first we have the n derivative of ln v over n. So ln v over n we could write as ln v minus ln n, and when we take the derivative we would get minus 1 over n. So we're going to have an n kb, and then we would get a minus 1 over n. Same thing for the second term. I could write this as 3/2 ln of mu over 3 pi h bar squared minus 3/2 ln of 1 over n. Minus 3/2 ln of n. And when I take the n derivatives, I would get minus 3/2 1 over n. So that's what we get. We get minus 3/2 1 over n. Okay. So I could take this n out front and cancel it with the two n's that are in there. And then I have a minus 1 minus 3/2, which is minus 5/2. And so all of this becomes minus 5/2 kb. But that minus 5/2 kb is going to cancel with the kb times plus 5/2 over here. Okay, and so that means that the chemical potential is equal to minus T times this derivative. So this is at constant U and V. And so what we're going to be left with is minus kBt, and then we have ln V over n plus 3/2 ln mu over 3 pi h bar squared n. And how do I get rid of this? There we go. And let's see if I can close this. There we go. Good. Okay, so now what I'm going to do is I am going to replace everything inside of the second ln with this 1 over lambda d squared, which we defined up top here. And then the v over n, I'm just going to make note of n, the number density of particles is n over v, so this v over n is 1 over the number density, and so that means ln of E over n is ln of 1 over n, or minus ln of n. Okay, and so our chemical potential then of our classical gas is going to be minus kBt times minus ln of the number density plus 3/2 ln 1 over lambda d. Okay, so if we distribute the negative sign, we have kBt ln of n minus ln, oh, so there should be a squared here. So minus 3/2 ln of 1 over lambda d. But I could take the 3/2 coefficient and change that to a power, so I have 1 over lambda d squared to the 3/2 power, which becomes 1 over lambda d cubed. And so we get 1 over lambda d cubed. We've worked with this quantity, lambda cubed, before, and remember what we did is this lambda represents kind of the spatial extent of the wave function of a particle in this gas. And so what we're going to be dealing with is lambda d to the cube to the power 3 is the quantum volume of a particle in the gas. And so in the classical limit, this is small. Remember when we were talking about Bose-Einstein condensation, what we required is, or one way to think of the condition for Bose-Einstein condensation was that this quantum volume had to become kind of bigger or equal to the space available per particle. And so the quantum volume grows as temperature decreases. If we're in the high temperature limit, this is small. So I'm going to define something like a quantum density, NQ, is 1 over lambda d cubed. And so if lambda d cubed is small in the classical limit, this is NQ is going to be large in the classical limit. At the same time we do all this, let's recognize that for a classical gas, N, which is the number of particles per unit volume, is small because a classical gas is one in which we assume there's no interactions between the particles, and so it's this dilute limit. And so this is small for a classical, which means non-interacting or dilute gas. Okay, so written in these terms, what we have is that the chemical potential is equal to kBt times the ln of the number density, which is small, minus the ln of this quantum density that we defined, which is large. And so combining everything, mu is equal to kBt ln of n over nq. And so this is the chemical potential of a monatomic ideal gas. Okay, good. So if we go back and we look at some of these expressions that we've written down for the Bose-Einstein and Fermi-Dirac distributions, a quantity of importance is mu over kBt that appears in these exponentials. And so what our calculation allows us to do is to write that mu over kBt is equal to the ln of n over nq, where n is small and nq is large. So for a classical gas, n is much less than nq, and so therefore what appears in these exponentials of the distribution functions is minus mu over kBt, and so that's equal to ln of, well, let's do it in a couple steps, minus ln of n over nq, which is equal to plus ln of nq over n, which is a really big number because nq is large and n is small. Okay, so if we go then write down the distribution functions, we'll remind ourselves of what they are. The Fermi-Dirac distribution function was e to the epsilon minus mu over kBt plus 1, and the Bose-Einstein distribution was equal to 1 over e to the epsilon minus mu over kBt minus 1. So the only difference is the plus or minus 1 in the denominator. So let's see. In the classical limit, what we have is e to the epsilon minus mu over kBt plus 1, which is e to the epsilon over kBt times e to the minus mu over kBt plus 1. Well, why don't we do plus or minus 1? That's what we should do, plus or minus 1. The plus is for the Fermi-Dirac distribution, and the minus is for the Bose-Einstein distribution. Well, we just said that minus mu to the kBt is ln of nq over n. So if we take the exponential of that, this is just nq over n, which is a large number. Okay, well, therefore, what we have is that the denominator is, well, let's just continue with our equal sign. So this is equal to e to the epsilon over kBt nq over n plus or minus 1. But because nq over n is so large, the plus or minus 1 doesn't matter, and this is approximately e to the epsilon over kBt nq over n. Okay, so therefore that means in the classical limit, the Fermi-Dirac distribution is approximately equal to the Bose-Einstein distribution, because what made them different was this plus or minus 1, but now we've gotten rid of that plus or minus 1, and so we just have to take the inverse of this expression to write down the distribution functions, and so it ends up being n over nq e to the minus epsilon over kBt. And so what we can conclude then is in the high temperature and dilute limit, the Fermi-Dirac, oh sorry, I'm not spelling that right. The Fermi-Dirac and Bose-Einstein distributions become identical. And that shouldn't necessarily come as a surprise, because when you take your, classical thermodynamics course, you never talked about the fact that there were bosons and fermions, and it was important which type of particle we were working with. It didn't matter. A gas of helium-3 and a gas of helium-4 behave in the same way in this classical limit. And so we don't need to worry about what type of particles these are in our gas. So the behavior of classical gas does not depend on whether the gas of particles is identical fermions or bosons. And so we could ask why that's the case. Well, this n classical is given by this expression that we just derived. So it's n over nq e to the minus epsilon over kBt. And so what this is telling us is the average number of particles in a state with energy epsilon at temperature T. Well, in the dilute limit, this n is small and nq is very large for the classical limit. And so what this is saying is that the average number of particles in a state with energy epsilon and at temperature T is always very small, right? And so you pick any random quantum state and you ask how many particles are in that state on average, and it's really, really tiny. And so then you ask yourself, well, if the probability of having a single particle in one of these states is really small, then it's exceedingly rare to have two particles try to occupy the same state at the same time. And if that's the case, then we don't really have to worry about the Pauli exclusion principle for fermions, because the chances of any two particles trying to be in the same state at the same time is really small. And so in that case, Pauli exclusion principle doesn't really matter. So in summary, regardless if one has bosons or fermions, the average occupation of quantum states is always much less than 1. And so that means whether or not particles need to obey the Pauli exclusion principle really isn't important. So it, let's say it becomes irrelevant. And so that's why your classical gases, we never had to worry about whether we had fermions or bosons. Okay, good. So that's it for today, and I will see you next time. Thank you very much.